the syllabus, the only missing jigsaw is probably negative numbers. How to represent them and how to do subtraction, for example. Okay? And then the syllabus is finished. Okay? So, typically, we have, let's say, a 7-bit, 8-bit rather. The 7-bit represent the sign. So, for example, if it is a negative number, the sign will be 1. Whereas if we have a positive number, maybe that sign will be 0. Okay? To know, for example, that this whole number has a sign bit in the first place, how can we know in terms of the AVR that the most significant bit of that 8-bit register contains the sign? How can we know in the Arduino, for example, which special register should we look at? Yeah?
Negative flag?
Negative flag, yes, but not quite. Negative flag tells us something, but there's another bit called the sign flag. So if you look at the status register and in the manual, you will see that it will tell us that actually this one is a signed bit and it is not the actual number. Okay? Now let's look at some examples. Now let's see that the most significant bit is the signed bit. So let's take 37. Here 37 is positive, so it is a 0 here, and the rest of them is the magnitude. Very simple. So the most significant bit carries the sign, and the remaining least significant bit carries the magnitude. For example, if I look at this one, this is, I think, is 32, plus 4 is 36, plus 1 is 37. Okay. Whereas for minus 39, that minus here is represented by a 1. Okay. And the rest of them corresponds to 39. So we had 37 here, and the only difference between this one and this one is 2, so 37 plus 2 is 39. Is there any questions on this? Or it's pretty obvious? Yeah? So we all know how to represent a negative number now, but it might create some problem in the case of, for example, you have a negative 0 and a positive 0. For us, in general, 0 is 0, right? So now we know that we can store that negative number in that kind of representation. Why would we want to use, for example, 2's complement? For those of you who know what is 2's complement. What is the importance of 2's complement? Which is this one. So 2's complement is another way to represent negative numbers in binary. So let's say you have a number. What you need to do is to make that number, take the 1's complement of that number, and then add 1. Does everyone knows what is 1's complement? No? How many of you did lab 5? Okay. What was that instruction in the AVR? What did that do? Yes, Paris?
It inverts all the zeros to 1, 1, 1, 0.
Yes, exactly. That is what is one's complement. Flips all the zeros to ones and ones to the zeros. That's one's complement. And then when you add 1 to it, it becomes 2's complement. As easy as that. Okay. So let's look at an example, minus 56. Okay. This is 56 in binary. Okay. I want to change that to minus 56 in 2's complement. The first thing I do is change it to 1's complement. So I flip all the zeros to 1. So 0 to 1, 0 to 1, 1 to 0. And then I add 1 to it. It becomes this number. Is that clear? This is the very, very first question in the exam. How many of you want me to go over that bit again? Okay. Maybe I should write on the board. Okay. We have 56. I say 56 is this. 0, 0, 1, 1, 1. I take for granted that you can convert 56 into binary, yeah? Or you want me to go over that bit again as well? Okay, everyone understands how to convert 56 to binary? Yeah? Okay. So at the moment it is positive 56. I want to convert that to minus 56, which is 2's complement. The first thing I do is I flip all the zeros to 1, so which means, so this becomes this, and then I add 1 to it. So 1 plus 1 is 1 plus 1 is 1.
0 carry 1.
0 carry 1. 1 plus 1 is 0 again. Carry 1. 0 carry 1. 0, 0, 1, 1. That is the representation of minus 56 in 2's complement. Is that clear? Yeah?
The thing I don't understand is that this number also represents the 200.
Yes.
How can we have two numbers?
Because here we're going to do, this number is 200. Why is it 200?
Because if you convert the binary to decimal,
The binary to decimal, you will get 200. Yes, it also represents 200. But in 2's complement, it also represents minus 56. Yes?
Then how would you know which one to the 200 or minus 56?
You don't know which one is which.
Well, if they're the same binary representation, I'm just thinking
Yes.
which one.
But you would, why would you want to represent minus 56 in the first place? When you are doing a
subtraction.
exactly. So normally you would only use 2's complement when you do a subtraction. Yeah. Otherwise you take that for, like you said, 200. So if we have 42, which is in hexadecimal, I want to know what is the 2's complement of 42. So this is not in decimal, it's in hexadecimal. I want to know how, first what should I do? I should convert that to decimal, or should I convert that to binary first?
Binary?
Yes. Once I have the binary number, then I convert that to 2's complement. So 42 in binary is 0, 1, 2, I think. Is that correct? 42 in binary? Or did I make a mistake? So this one represents 4 because it's 1, 2, 4. 1 and 2. This one represents 2. And I need to represent that in 2's complement. So the first thing I should do is flip all the bits. And then add 1, right? So this is the answer C. Let me see if I add 1 to it. 0, 1, 1, 1. And the rest is the same thing. It is C. Yes, it is. How many of you want me to explain that bit again? That's a mistake, I know. But how many of you want me to explain that bit again? Anyone? No? Okay. So I think you've got it now. You flip all the bits and then you just add 1. Now, can you use 2's complement to do that subtraction over here? have one, and then we need to subtract the other one, which is 1, 0, 0, 1, 1. I would like a volunteer to do 2's complement of this one. Anyone? How about this at the back, Nikhil? Can you come on the board and do 2's complement for me? No? Too scared? James? No? Okay, Paris. Thank you. Two's complement, yeah. Not for this one. For this one. Because this one is a negative number. Thank you, Paris. Did everyone got that? Everyone understand what Paris did? I can see blank faces, so I can't know whether you've understood or you haven't. Yeah? So what he did was to flip all the ones to zeros and zeros to 1, and then he just added 1. It is this number. Okay, so now we got this number. 0, 1, 1, 0, 1. We add them. 0. I think 1 is here. 1, 0, 1. 1 and 1 give me a 0. And then I have it carry forward here, right? Or did I get that wrong? Everyone agrees with that? Please tell me whether you agree or you disagree. You agree? But I don't have this number in here, do I? Let's see what. Wow, 95% have said yes. Yes, it is this one. So for the subtraction, okay, you ignore the carry bit. Coming back to the previous one, we did find this one, right? As 2's complement, didn't we? So I was wrong, because my answer said it is A, right? So am I still wrong, do you think? How many says my answer here is wrong? Hands up. 1, 2, 3, 4, 5, 6, 7. How many of you say that here my answer is correct? 1, 2, 3, 4, 5, 6, 7, 8. 50-50. It's a tight one. For positive number, which is in this case, 2's complement is itself. You have to do this. On a negative number, you do have to do the flipping and the addition of 1. Now coming to Lampro's question, when do we know this one is 2's complement? When do we know that it represents 100? In terms of the hardware itself, okay, how do we know that a number is a negative number? So in your Arduino, how would we know that the number in a register is a negative number? Yes?
In the status register is a negative.
Yes. So you look at the status register. Okay, that's the first one. But in terms of implementation of that subtraction, if you want to do a subtraction, okay, where you would have a negative number, then you would use 2's complement. Why would you use 2's complement instead of actually doing straightforward the subtraction? Is because we can use the same logic gates that you learned in week 2 or 3, I don't remember, to perform the same subtraction using the same circuit. You don't need another kind of circuit to do the same, to do a different operation, which is the subtraction. So in terms of storage, okay, we have the negative bit, but when you actually do the actual subtraction, the hardware will be using 2's complement. Is that clear? So this answer is correct, it's A. But I just wanted you to think about it before I gave you the right answer. Okay? So you've learned about, you're probably learning now Java, right? When I was studying, I was probably doing this one. Probably not, lots of you haven't studied this one. But like I told most of you, I failed my first programming test. So I think most of you also have failed probably the first programming test that was in week 0. But that doesn't mean that you will fail the whole module. But coming back to this course, normally you would have a high-level programming language, and you would have a compilation process, and then you would get the machine code. What does that mean, the compilation process? What is this actually doing? Yes?
Is it changing it so that the machine understands?
Yes. It is changing your code into something that machines can understand. That's what is compiling your code. So obviously you will typically have binary numbers, but in terms of the Arduino, do we actually upload binary numbers, or do we upload other kinds of numbers onto the Arduino? How many of you have done that night? Yeah? So was it uploading binary numbers, or was it uploading something else? Yes. So in the case of the AVR, we are actually uploading the hexadecimal numbers. But what I want you to know, the difference between compilers and interpreters. What's the main difference between the two? One is actually converting everything to machine numbers. Okay. The other one actually goes line by line, convert each line into a machine code, and then you do the processor execute the instruction. That's the main difference between the two. But we know that, for example, in the assembly language, we don't really use, for example, the virtual addresses. So you have more direct connections with the hardware. So and the other thing is, if you do lab 9 today, you will see that all the instructions are converted easily into hexadecimal, and the hexadecimal is very easily close to the binary numbers, which is the actual machine code. Okay. So I think we've finished the syllabus. Next week, I will give a revision lecture with all the quiz that we have been doing throughout the whole semester. I will not be introducing any new materials, but you are strongly advised to come. Okay? Okay, now it's 10:35. I can go over the coursework, or we can go to wherever we want now. How many of you want me to explain a bit about the coursework, or at least give you a hint? Wow, overwhelming, yes. Okay. Concerning the coursework, if you look at the mark scheme, okay, you can get almost 60% if you do everything well, if you implement only 2 letters, and that 2 letters is E and T. Did you realize that? Nobody realized that? Everybody wanted to implement everything in one go? That's the very, very wrong approach. Okay? If I were you, first of all, I would consider the implementation of E and T, get it working, and then if I have time, implement the others. Because if you want to implement everything, then you will run out of time maybe, and you will not be able to implement the coursework at all. That's what happened in last year's in my module. Lots of them wanted to do everything. In the end, some of them failed because they wanted to do too much. Okay. The other thing is, I had another question was, one, you have also to implement the Morse encoder in AVR. So that's 10% to make it 100%. But everything else is understood that you have to implement in assembly code. Yeah? So the decoder, which is the main coursework, is in assembly. You should not implement that in C. If you implement that in C, you will not get any more at all. Okay, let me look at my notes now. How many of you have done lab 8? If you've done lab 8 and you, let's say 80% understand what's going on, you should be able to start and finish the coursework today itself. Okay? Lab 8 is almost the solution to the coursework. So let me see at my notes. I heard also one group is almost finishing, so I think next year I should give a more difficult coursework. Because 2 weeks before the deadline you have already finished. Okay? So if you look at, I'm going to talk in the context of lab 8. Okay, so that you can implement E and T. So last week, for those of you who stayed, I mentioned something like this. If the button is pressed, okay, what should that be? What else can I do? So if I press the button, so if I look at the signal, when is the button pressed in here? Is it here? Is it here? Is it here? What is it?
When is the falling?
Falling edge, right? That's when I know when my button is pressed. But when my button is pressed, then it should mean two things, right? What two things it should mean in terms of the force word?
Delay.
Yes, it starts counting from how long it's pressed. It counts how long it's pressed, yes. But in terms of the Morse code,
Dots and dashes.
yes. Once the button is pressed, it only means two things. It's either a dot or a dash. Okay? So, to differentiate between the two, if the time, once it is pressed, after it is pressed, if the time is less than 200 millisecond, then it is a dash or a dot.
Dots.
Yes. Otherwise, it is a dash, right? So what is the interrupt flag that I should be looking for to detect that falling edge? Do you know the flag, the name of the flag? Does this sound familiar? Yeah. So when this is set to 0, I think, that's when it detects the falling edge. Otherwise, when it is set to 1, it detects the rising edge. That's how you would know if the button is pressed. Okay? So that 200 millisecond here, I had a variable in lab 8. Do you know the name of that variable in lab 8? What was it called? Yeah?
The timeout one.
No. So if you go back to lab 8, you look through my code, it was something called the decision limit. Okay? That was how I got 200 milliseconds in the decision limits. Now, we might have two different, we need different timings, right? So if we have A and E. What is the Morse code of A and E? What is the Morse code of A? Can someone look it up?
Dot dash.
Dot dash. And E is this one, right? I had a spacing between here and I have a spacing between here, right? This one, I think I set it to, what was that? What was the timing? 100 millisecond?
Point.
Was it 100 millisecond? And that 100? And this one was 700? Yeah? So, once I've pressed this, the next thing that comes, okay, the next button that is pressed, you would have that gap over here. So the easiest way is if button is released, which means this one, And if, that's my way of implementing it, doesn't mean it is the only solution. Okay? If the time, for me I put less than 400 milliseconds, then it means it is this gap over here. I call that intersignal gap. Otherwise, it is the interletter gap. Is the gap between this one and this one. And also for how do, yes?
What about the gap in between words?
Between words. No, I'm not going to talk, I'm not going to send a word, just different letters. That 400 milliseconds here, I already had it in lab 8 as well, if you did lab 8. What was the name of this? It was what Paris said. I think that was it, time out, I think. That was the name of my variable, that 400 milliseconds. So you see lab 8 is almost the solution to the coursework. You're not starting from scratch. Okay? But in the context of E and T, okay, the only thing that you really have to worry, or the easiest way to implement it, okay, is in the lab 8, in the very, very last line, you have something called long press. There's a label called long press, and there's another label called short press. That's ENT for you guys. Yeah. So if you have, can I erase this or, yeah? So if you go back to lab 8, you would have a label called long press. Okay. In that long press, in the original code, you would have something called load R16, and then you would call DV red, DV button, what you need to do for the coursework is just substitute this bit here with something along this line. For example, LDI R16, and then to switch on the LED, 7-segment LED. So for example, if it is a long press, it is a T, right? Because T is dash, T is dash, and E is dot, right? So it would be something like this. You have the tilde, and then the corresponding 7-segment for T, where you would have minus dB, whatever you have, whatever segment you want to light up on the 7-segment display. That's where you can modify lab 8 to get the coursework. And then for the short press, it would be again be the same, but for putting letter E on the 7th segment. So that's lab 9. Now, I had another query. You have only 7 segments, but you need to display 26 letters. So for example, some people told me they don't know how to display M on a 7-segment display. For example, M, I can do something like this. You have letter N here, and maybe a dash to say that it is double N. It doesn't need to be exactly M, but that can be my letter N, for example, on the 7-segment display. Okay? And I take it that it's on port D that you will switch on the 7-segment display. Yeah, it's not on port B. So at the moment in lab 8, it is port B. So you have to change that as well. And you also have to use something like this, AD or D, to enable port D to be able to display on the 7th segment. And that's the solution to your coursework. But that's just for the single letter. So I'm kind of giving you free 60%. It's up for you to get the other 40%. Okay? Okay, I'll see you today.